Welcome to Statistics 1 Lab 5. The goals in today's lab we'll repeat a lot of the steps that we've done in previous labs. So we'll read a data file into R, we'll print some summary statistics. But the emphasis this week is on null hypothesis significance testing, as well as standard error, confidence intervals, and model comparison. So we'll do correlation and regression analyses again, but emphasizing significance tests and the problems with significance tests and how to supplement them with things like confidence intervals and model comparisons. And I'm going to use the same example that I used last week, the correlational study investigating the predictors of physical endurance in adults. The outcome variable is physical endurance. The predictors are age and number of years actively engaged in exercise. The initial analyses are the same as last week, so we're going to assume a sample size of 200, but then to show you the importance and the impact of sample size, I'll reduce that. I'll take a random subset of the 200, just 20, and then we'll rerun the analyses. Again, I've commented out all this beginning stuff, so just make sure you're in the right working directory. You might need to install a new package here. We're going to use ggplot2, which we'll use a lot going forward in the course. It's sort of the premier graphics package in R. So go ahead and install that package. And I'm going to start right here. I'm going to load my packages with the library function. I'll read in the data. I don't need to look at it because we've seen this before. But then I'll run the describe function just to get the summary statistics. So here are the summary statistics, and this is what we saw last week. We have 200 subjects with a mean age of about 49, active years about 10.5. Endurance, remember, was this scale that went from 0 to 60, an arbitrary scale. But we did all that last week. So let's quickly go back to the script. In this lab, I'm going to illustrate some of the calculations of these values because we're not doing a lot of hand calculations, which is different from my live class. So I just want to show you where these numbers are coming from. So just in that describe output, you saw standard error. So standard error, if you look at this line here in my script, standard error is just the standard deviation divided by the square root of sample size. Remember, standard error is just how much sampling error on average do we expect. And this is the formula. So standard error is standard deviation over the square root of n. So what I can do in R is I can take that describe function and I can save it into a table. I'll call it table 1. And if I do that, let's execute those 2 lines of code. Then I just have table 1. It's the same exact thing as I just got from the describe function. But now I can access the values inside that table, which becomes really handy, and we'll do this a lot going forward. So for example, if I want the standard deviation for the age variable, then I could just go into the table and go to row 2, column 4, because that's where standard deviation for age is. And if I want the sample size, I can go to row 2, column 2. So let's just execute those. So the standard deviation for age is in this table, and it's in row 2, column 4. So if I go to row 2, there's age, and column 4, 1, 2, 3, 4, there's standard deviation. Okay, so it's going to return 10.48. And the sample size for age, well, it's the same for all the variables, but it's table 1, row 2, column 2. So row 2, again, age, column 2, 200. The reason I'm showing you that is we don't need to do this because R gives it to you in the describe function, but you could calculate the standard error of age based on those values. So I could just calculate the standard error of age based on the standard deviation and the square root of the sample size. So if I execute that line of code, I get 0.74 for the standard error of age, and if we go back up in the table, yep, there it is. So we did the calculation correctly. Just to be really sure, I could test it and see if my calculation equals table 1, row 2, column 13. That's where standard error was. So if I execute that, I get true. Okay, so we did it right. The point of that is to illustrate that you can save output in R into tables, like I did here, save it into table 1, and then you can access the values in that table to do calculations. And that's going to be handy going forward. Okay, so let's go back to the main topic, correlation regression. We ran this correlation analysis last week, but what we didn't do was core.test. So we can run a null hypothesis significance test on each of these correlations to see if they are statistically significant. In other words, the null hypothesis is that the correlation coefficient is 0, and this will give us a p-value, which stands for the probability of obtaining this correlation given the assumption that the null is true. So let's see what we get from these. Let me go back up a little bit. So remember, these are the same data from last week. So we had like correlations of 0.33 between age and active years and between endurance and active years, but then not much going on between age and endurance. Here's the output for core.test. It gives the Pearson product moment correlation. Here's the correlation, 0.33, and here's the p-value. So it's a very low p-value. That's significant. Same is true for the correlation between endurance and active years, 0.33, low p-value. But then for endurance and age, that's a correlation of -0.08, and that's a p-value of 0.23. So there we would have to retain the null. That's not a statistically significant correlation. Okay, I'm going to save those correlations into a table, table 2, because we're going to use them to illustrate some calculations in the regression analysis. So let me just save that, table 2, go back into the console. Looks like it did it fine. Great. Okay, let's move on to the regression analyses. I'll start with unstandardized regression analysis, just a simple regression. Again, we did this last week, so I'm going to try and go through this quickly. So here is that first model predicting endurance from age, and of course, that's not significant. And if you notice, the p-value here is 0.232 for that regression coefficient. It's the same exact p-value as up here for the correlation coefficient. Right? That's true because we're just doing a simple regression with one predictor. But now let's illustrate some calculations again. So how would we calculate that regression coefficient? Well, I talked about it in lecture where I talked about calculating the sums of squares residual and the sums of squares for the model and so on. But another formula I gave you for the regression coefficient is this formula right here. The regression coefficient can be calculated by taking the correlation coefficient and multiplying by the standard deviation of y over the standard deviation of x. Well, I have all these values now in tables, right? So in table 2, that's my correlation matrix. I'm looking at the relationship between age and endurance. So let's go back into the console here. If I look at the correlation matrix, it's going to be row 3, column 1 to get this correlation coefficient for this model. So that's why I get row 3, column 1. So the model's regression coefficient, model 1's B, is the correlation coefficient, which is in table 2, row 3, column 1, times the standard deviation of y, which is in the first table, row 4, column 4, and the standard deviation of x, which is in row 2, column 4. So let me just execute all of that. And what we see here is we calculated a regression coefficient of -0.08. If you go back up into our output from the LM, that's exactly what we get. A little bit of rounding error, but we did it right. So here's just illustrating how you can calculate these values from the basic formulas that I gave you in lecture, rather than just relying on the LM function to give it to you. It just helps to sort of understand this at first. Of course, you'd never do this piece. Again, this is just to help you learn the concepts and learn the math underlying linear regression. Okay, so now let's look at how the standard error is calculated. So standard error of a regression coefficient it's a little bit more difficult, the formula. It's not quite as intuitive, but here it is. It's the square root of the sum to squares residual over n minus 2 divided by the sum to squares for x. So I've written it sort of in notation form here. Standard error for the regression coefficient is the square root of sum to squares residual over n minus 2 divided by sum to squares for x. I'm going to create one more table here using the ANOVA function. And that's going to give me the sum to squares residual. Of course, we could calculate it by hand, right? We could go through all 200 subjects and get their predicted score and their actual score and get the residual and square it and sum it. But that would be pretty tedious, and this is going to be a long lab anyway. So let's just use that ANOVA function. So what the ANOVA function returns are these sum to squares for the model. So if you think back to lecture where I talked about sum to squares for a model and sum to squares for residual, this is sum to squares for the model. This is sum to squares residual. So we're going to use this value to calculate standard error. So sum to squares residual is in table 3, row 2, column 2. Just to make sure we did that right, let's execute that. Right, so there's the table, row 2, column 2, 23,000. I now want to divide that by n minus 2. Well, that's degrees of freedom, and we'll talk a lot about degrees of freedom when we cover analysis of variance. But for now, in this example, it's just n minus 2. So that was in the table. It's in the row 2, column 1. So let me just grab that. So if you look at this table, row 2, column 1, remember there are 200 subjects, so 200 minus 2 is 198, and there I have that value. The sum to squares for x, the entire value, variable x, is the sum to squares for the model and the sum to squares residual. So I can go back into the table in column 2 and just take row 1 and row 2 and add them together, and that'll give me sum to squares x. So let me do that. So now I have sum to squares x. It's just the sum of, just the sum of this column here. So now we can calculate the standard error of the regression coefficient. It's the square root of the sum to squares residual, which we got from table 3, which we got from running the ANOVA function. Degrees of freedom also came from that ANOVA table, but we could have just plugged it in. It's total number of subjects minus 2. And sum to squares x, again, we got from the ANOVA table. It's just the sum to squares for the model plus sum to squares residual. So now if I do that, the standard error for the regression coefficient, according to our calculations, is 0.07. If we go back up to where we ran the LM function, you see the standard error is 0.07. Great. So we did it right, and it matches up. Again, going forward, when you do multiple regression, you're just going to rely on this LM call, and you're going to rely on R to do the calculations for you. But I think it's nice to go through this once when you're first learning it to see where the numbers are coming from. Okay, so now let's move to confidence intervals. It's really easy to get confidence intervals in R. So if I want the 95% confidence interval around that regression coefficient, all I need to do is use the function confint. So confint around model 1. You can use the confint function around any fitted model. So if I do that, it returns the 95% confidence interval for the regression constant, but also the regression coefficient. And that's what we really are concerned with, is this interval. All right, so it goes from negative 23 to positive 0.05. The fact that it spans 0 indicates to you that it's not going to be a significant regression coefficient, okay? Because we are in the 95% confidence interval is included 0, no relationship. So that's a sign right there that we're going to retain the null and that this is not significant. We could also illustrate the calculation of that confidence interval. So the upper value of a confidence interval, to get the higher value, you take the regression coefficient and you add a product term, which is a function of standard error. It's just standard error times some critical t value, which is based on degrees of freedom and the degree of confidence. It turns out there's a really nifty way you can get that in R using this qt function. So I combine 0.025 and 0.975 because that puts 2.5% of the distribution on the lower end of the sampling distribution and 2.5% on the higher end. And then my degrees of freedom is 198. So right here is where I'm telling it that I want 95%. Here is where I'm telling it what degrees of freedom are. And remember, I have to indicate degrees of freedom because remember there's a family of t distributions and they differ slightly according to sample size and degrees of freedom. So this t-crit value depends on not just the degree of confidence, but also degrees of freedom. So let me run that. And that t-crit value is about 1.97. In a perfect Gaussian distribution, a perfect normal distribution, the z distribution, that corresponds to 1.96. So we're pretty close because this is a large sample size. It's just a little wider. So now I could calculate the interval as the regression coefficient, which was negative 0.08, plus t-crit times standard error, and I get my interval. Negative 22 to positive 0.05. That's the same thing we got when we ran the confint function. A little bit of rounding error. Again, we'll never do this piece again. We'll just use the confint function. But again, I wanted to illustrate where these numbers are coming from, and that's the formula right there. Okay, let's go back into the script. Now we're going to just look at the scatter plot again, but now we're going to make use of these fancier graphics that exist in the ggplot package, and they're really cool. And what I like about this scatter plot, and I really encourage my colleagues and my collaborators to do this, is to plot confidence intervals around a regression line. Because remember, a regression coefficient is just a point estimate, and it's susceptible to sampling error. So we should be explicit about that in our graphical representation of the correlation and of the scatter plot. ggplot allows us to do that. So let's see what it looks like. And there we go. That is very cool. So I plotted age on the x-axis, endurance on the y-axis. Remember, the dots are all just individual participants. And they're sort of all over the place because there's not much of a correlation here, right? It was like negative 0.08 or something. So there's a slight negative slope. But notice this shaded region around it. That represents the 95% confidence interval around that regression coefficient. And that's a really nice thing to do when plotting scatter plots. And unfortunately, it's just not done enough at least in the social sciences. But hopefully we can encourage people to do this more often. 'Cause I think it looks pretty cool. Okay, so now let's look at Model 2. I'm not going to go through all these illustrations of calculations again because that takes a while. And we did this last week. So let's just print the output of the model and the confidence intervals. So here we're predicting endurance from active years, and the t-value for that regression coefficient is 4.8, and that's significant. Right? We're now explaining about 11% of the variance, and if you look at the confidence interval, it goes from about 0.44 to 1.06. So 0 is nowhere near that 95% confidence interval, another sign that this is a significant predictor. Let's look at our cool new scatter plot with the confidence interval on it. Nice, there we go. We got a nice, strong, positive correlation, and we put in the confidence interval around the regression line. Let's quickly just move through Model 3. We did this last week, so I'm just going to zip through it and just show you the plot. There we go. The slope is a little bit steeper here, because if you go back into the output, we're now explaining about 15% of the variance. So we're doing a little better by putting both predictors in than by just putting active years in. And the final thing we can do is conduct a model comparison, an actual null hypothesis significance test, to determine whether Model 3 is significantly better than Model 2. And it's real simple. We use this ANOVA function again. So we just do ANOVA Model 2, Model 3, and that will give me a p-value indicating whether I should reject or retain the null hypothesis, where the null hypothesis is that Model 2 and Model 3 are equivalent in terms of how well they explain the outcome variable. So here's the output from that model comparison line of code. And here it gives us an F statistic, which we're going to talk a lot more about when we get to analysis of variance. So just bear with me here. I'm going to gloss over some of the details. But it's a lot like the T statistic. You get a certain value, and then it has a corresponding p-value based on a sampling distribution. Again, we'll talk about this more in depth when we cover ANOVA. But the key point here is that the p-value is less than 0.05, so we can say that the difference between Model 2 and Model 3 is statistically significant. So Model 3 is doing better. Also notice that this p-value is exactly the same p-value as the one for age when age was added in with active years, because that's the difference between Model 1 and Model 2, right? So it's the same thing. Okay, now let's go back to the script. I just want to show you the standardized solutions. Again, we did this last week, but I just want to run through it and show you the confidence intervals. I'm going to run them all at once because I want to get through this so we can move on to the final part of the script. So here's where the standardized regression analyses started. The thing to notice in the standardized is the regression constant is always right around 0. I mean, this is out to 18 significant digits, right? Oops, didn't want to do that. But it's 0, right? We're standardizing it so that the intercept is 0. But if you look at, say, the model R-squared, percentage of variance explained, that's exactly the same. And the width of the confidence intervals, those will be exactly the same. It's just the intercept that changes. Okay. So just to drive that point home, we could do that same model comparison to compare Model 2 and Model 3 standardized, but you're going to get the same exact thing that you got before, right? So let's run it. So here's the standardized model comparison. Here's the F value and the p-value, that same p-value, 0.002. Just to show you it's exactly the same, I reran the unstandardized. There are the values. Okay. The sum to squares, those change, right? Because I changed the scale of the variables, but the F ratio and the p-value are exactly the same. Okay. Okay, so the last thing I want to do in this lab is now just radically reduce the sample size. So we had a really nice sample size of 200. Now let's cut it down to 20 and see what happens to some of these significance tests and confidence intervals. So I'm just going to take a random sample of 20 from this data frame PE, and I'm going to call it PE20. And the way to do that is to use a function called sample, and I'm just going to take out 20 rows. I still want all the columns, I want all the variables, but I just want 20 subjects. So I'm going to do that and run the describe function. And now I have just 20 subjects. And you'll notice that the standard errors are a lot larger because there's more sampling error if we're only getting samples of 20. So what happens with the correlations? Remember, this is just a random sample of 20, so I'm not sure what the actual correlation values will be. Let's see. Let me go back up in the output. Pretty close to before, although now we got a 0.2. So we got 0.33, 0.38, and 0.2. This was randomized differently each time, so I wasn't sure what I was going to get there. It's sort of nice that we got a 0.33, right? Because we had 0.33 with an n of 200. So let's go to that 0.33 with an n of 20 and see if it's significant. So age and active years is right here. And there's that 0.33, and here's the p-value. It's 0.16. So the same exact magnitude correlation, 0.33, is now no longer significant with an n of 20. That's because the standard error is higher. So again, this illustrates one of the problems with null hypothesis significance testing is it's biased by sample size. That same exact correlation coefficient before we could have claimed was statistically significant with an n of 200. Now with an n of 20, we can't. So that's a little bit funky. Even here, a correlation of 0.38, still not significant. The p is 0.09. Okay, so when you're doing correlational analyses or correlational studies, you typically need large samples. Now let's look at what happens to the regression models. So again, I'm just going to run all of these at once because I think you get the gist. Let me go down to model 3, model 3.20, which has both predictors in the equation. And if we go to the table of coefficients, what we see is neither one of them is significant. So remember, that's different from before. When we had an n of 200, both of these were significant. Now neither one is significant. Also notice the confidence intervals are much, much wider. Again, that's because the sample size is so much smaller. We expect more sampling error. We have a higher standard error, wider confidence intervals. Okay, finally, let's just do that model comparison. And you guessed it, it's not going to be significant. So the F is really low, and we have a p-value of 0.7. So now I can't claim that model 3 is any better than model 2, even though it does account for a little bit more of the variance in the outcome variable. But again, that's because we don't have a sufficient sample size with 20 to detect statistical significance and reject the null hypothesis. So again, that's the importance of sample size when doing NHST. And that, I believe, wraps it up. So this is all you'll need to do assignment 5. Again, it'll be on correlation and regression, but with an emphasis on model comparisons and confidence intervals. Good luck on that, and I'll talk to you next week.